So here's 8.2. And we've already talked about this. What we've been dealing with has been one mean. So we're going to break this into two parts. Part one, if you have a large sample, in other words, your sample, your n value is greater than 30, then that means it is normally distributed. And you can just calculate using a z-score, okay? However, if your population is less than 30, remember we talked about small sample sizes, then we can't use the z-score. Instead, we need a t-score. And you've seen this before. Remember when we talked about degrees of freedom and how if you have a small sample, that normal curve gets squashed down and the tails go up a little bit and your area's all changed? Well, same thing happening here. Here again is the description of the degrees of freedom for small sample sizes. And so if you do a t-score, you need degrees of freedom, and then you also need your confidence level. And you would use these two things to determine your t-score, which is just a modified z-score, right? So we did all of this back in chapter 7 when we looked at this with big populations and small populations. That's the only wrinkle. Everything else is exactly the same as what we did before in 8.1. So you establish the population mean, the population standard deviation. You get your sample mean and maybe your sample standard deviation and then the sample size. If your sample size is greater than 30, you use the z-score. If your sample size is less than 30, you use the t-score. Okay? So once you're done with that, you set your null hypothesis, and then you pick one of these. So pick one. Are you above, or pardon me, are you looking for the area less than, greater than, or not equal to? And then you pick one of these. What is your threshold? 1%, 5%, or 10%? And all of this information will be sort of given to you. You just got to make sure that you can identify it. And so then you make sure that a random sample is taken. You verify the sample size. Do you use the t-test or the z-score? And here again is the z-score and the t-score. A lot of people just use the t-score because at sizes greater than 30, the t-score is the z-score. So they're kind of the same thing. So you're going to have this normal distribution. That's your population mean. This is going to be your sample mean or your target. And then in this case, let's say you wanted to find the area below. This is your p-value, the probability. You're going to take this p-value and you're going to compare it to alpha. So p-value compared to alpha, where alpha is your significance level. Is it greater than? Is it less than? And hopefully if it's less than, you get to reject the null hypothesis. Yay. If it's greater than, you fail to reject the null hypothesis. Boo. That's not what we want. And then you write up an interpretation. So here's an example. The life expectancy of European men from 2020 is 70.8 years, 79.8 years. So this is our null. That's the population. The life expectancy of 53 random European men from 1960 are listed below. So here are our sample. Okay. Do European men from 1960 have a lower life expectancy than 2020? Test it 1%. Lower means less than. So is the mu from 1960 less than the mu from 2020? That's what we're checking, okay? Less than. So here we go. Life expectancy is that and that. Here's our null hypothesis. And our alternative hypothesis is we think that it's less than, right? The life expectancy is less than. And we're checking at the 1% level. So here's some information. If we go out and we take that sample of ages, right here, this sample of ages from 1960, at life expectancy, we should say, you will find that that sample has a mean of 73.74, a standard deviation of this, and a degree of freedom of this. You place those into the t-score algorithm, and it generates a t-score of this. So what does that mean? That means that the average life expectancy from 1960 is nearly 7.7 standard deviations below the mean of 2020. So you're thinking like this, and here's the 2020 mean. And if you go 1 standard deviation, 2 standard deviations, 3, 4, 5, 6, 7.71 standard deviations away, that is where 1960 is. So my guess is this is going to be a very small area under that far left tail. And so go to Desmos, here's a graph. Oh, look at that. And you can barely even see it. It's actually there. This is the area that we want to find, this little area. And there is the calculation from Desmos. This is a very, very, very small number. We can do the same thing using Google Sheets. So you punch in your information, bing, 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 bing. And again, here is your p-value, a very, very, very small number. So our p-value comes in way below our 1% threshold. So our p-value is less than the significance level, which means we can reject the null hypothesis that the life expectancy for people in 1960 is 79.8, and we can replace it with our alternative, which says that the life expectancy for male European men in 1960 is much less than the life expectancy in 2020. So here's the TAC tool, and you're going to punch in the population mean, the significance level, the sample size, the mean of the sample, and the standard deviation of the sample. All this then is going to be calculated to give you your degrees of freedom, your confidence level, the z-scores of a one-tailed and a two-tailed, and then the test statistic, and then the areas. And so you can use this to answer the questions from 8.2.